Look up at the night sky. What do you see? A vast, seemingly random scattering of stars. Now, picture this. What if every spiral galaxy, every swirling nebula, even the tiniest quantum particles humming in the void, all follow a hidden pattern? A cosmic blueprint so precise, it echoes in the petals of a flower and the curve of a seashell. That's the magic of symmetry, nature's quiet secret, written into the fabric of reality itself. From the golden ratio stretching across galaxies to the eerie perfection of snowflakes, our universe whispers order in a language we're only beginning to decode. And here's the thrilling part: these aren't just beautiful accidents. They're clues that could unravel everything we thought we knew about space, time, and the very laws of physics. Symmetry isn't just about mirror images or perfect shapes. It's the backbone of the cosmos, the rulebook the universe plays by. Think about it. The same forces that sculpted the spiral arms of the Milky Way also dictate how electrons dance around an atom. It's as if the universe has a favorite recipe, and it keeps using it, from the unimaginably large to the invisibly small. But why? That's where things get wild. Some scientists believe these patterns are echoes of higher dimensions or shadows of a deeper, more fundamental reality. Others argue they're proof of a cosmos far stranger than we've dared to imagine, one where symmetry isn't just a feature, but the very engine of existence. Ready to have your mind stretched? Over the next 30 theories, we'll journey through the most breathtaking ideas in modern physics, from the elegant to the downright bizarre. We'll explore how black holes might be perfect spheres of pure symmetry, why some researchers think the universe is a hologram, and whether time itself could be an illusion woven into these hidden patterns. This isn't just science, it's a detective story on the grandest scale, and you're invited to piece together the evidence. So buckle up. By the end, you might never look at a star, a snowflake, or even your own reflection the same way again. The cosmos is speaking. Let's listen. Imagine a cosmic mirror where every particle we know has a secret twin, a shadow version of itself, lurking just beyond our detection. That's the heart of supersymmetry, or SUSY, one of the most elegant ideas in modern physics. It suggests that every fermion, the building blocks of matter like electrons and quarks, has a boson superpartner, and every boson, the force carriers like photons, has a fermion twin. Picture electrons paired with selectrons or photons with photinos. These aren't just whimsical names, they're potential keys to unlocking the universe's greatest mysteries. Why would nature need such symmetry? Think of it like a cosmic balance sheet. Fermions and bosons behave wildly differently, yet SUSY proposes they're two sides of the same coin. This elegant pairing could solve some of physics' biggest headaches. Take dark matter. If photinos or neutralinos exist, they'd be invisible, massive, and everywhere perfect candidates for that elusive cosmic glue holding galaxies together. Even more tantalizing, SUSY might unify the fundamental forces. At high energies like those just after the Big Bang, it could reveal a single harmonious force behind electromagnetism, gravity, and the nuclear forces, a theory of everything written in the language of symmetry. But where's the proof? For decades, scientists have hunted for these superparticles using the most powerful tool we have, the Large Hadron Collider. Smashing protons at nearly light speed, they've scoured the debris for signs of squarks, gluinos, or any SUSY echoes. So far, the universe hasn't handed us that smoking gun. Some researchers worry SUSY might be a beautiful idea that doesn't match reality, while others argue we've barely scratched the energy scales needed to find it. It's like searching for a whisper in a hurricane. Our tools might not yet be sharp enough. Yet even without direct evidence, SUSY mathematical elegance keeps it alive. It's a reminder that sometimes the universe hides its deepest truths in patterns we're only beginning to trace. Whether SUSY is confirmed or overturned, it's reshaped how we see reality. not as a collection of random particles, but as a symphony where every note has its harmonic counterpart. And if that's true, the cosmos might be far more balanced, far more beautiful than we ever dreamed. There's something almost poetic about how supersymmetry dances through the equations of modern physics. If you could peer into the mathematician's notebook, you'd see symmetry transformations unfolding like an intricate ballet partner swapping places, operations mirroring each other with perfect precision. This isn't just abstract beauty, it's a language that connects quantum mechanics to the cosmic scale. Take string theory, for instance. SUSY slots into it like a missing puzzle piece, allowing strings to vibrate through 11 dimensions without mathematical contradictions. Picture those extra dimensions curled into Calabi-Yau shapes, tiny, 6-dimensional geometries where symmetry isn't just present, it's mandatory. These manifolds aren't random. They're mathematical sculptures where every curve and fold respects SUSY elegant rules. What makes physicists cling to this idea despite decades without experimental proof? Imagine building a bridge suspended by invisible cables. You can't see them, but without their tension, the whole structure collapses. SUSY does that for modern physics. It stabilizes the Higgs boson's mass, preventing quantum corrections from ballooning it to impossible sizes. It smooths out the jagged edges between gravity and quantum forces, offering a path to unification that simpler theories can't match. Even the standard model's messy particle zoo starts to make sense when viewed through SUSY lens, like finding every chaotic star constellation actually fits a grander celestial pattern. Visualizing these symmetries feels like decoding the universe's hidden blueprints. On a whiteboard, SUSY transformations might look like flipping a chessboard where pawns morph into queens fermions becoming bosons and vice versa. But beneath the symbols lies a deeper truth. Nature might not care about our human distinctions between matter and force. At the highest energies, where particles lose their identities like ice melting to water, SUSY suggests everything emerges from a single symmetrical origin. That's why researchers keep refining particle colliders and scanning cosmic rays. They're chasing more than just unseen particles. They're hunting for the signature of a universe far more harmonious than it appears. The irony, SUSY's greatest strength, its flexibility, also makes it elusive. Like a melody transposed into infinite keys, the theory allows superpartners to hide across vast energy ranges. Some versions predict particles just beyond current collider reach. Others place them in realms we may never access. Yet even if SUSY remains mathematically beautiful but physically unconfirmed, it's already reshaped physics. It taught us to look for deeper patterns, to question why nature separates matter and force at all. And perhaps that's the real revelation. Sometimes the search for symmetry leads us not just to answers, but to better questions about reality's true architecture. What if everything you see, the stars, your hands, even the screen in front of you, is nothing more than an illusion, a high-resolution mirage projected from the edge of space itself? That's the radical idea behind the holographic principle, a theory so mind-bending it suggests our three-dimensional universe might just be a cosmic movie playing on a two-dimensional surface. Think of it like watching a 3D film at the theater. The images feel real, immersive, but they're actually projected from a flat screen. Now, imagine that screen isn't made of plastic and pixels. It's the boundary of our universe, a thin membrane where all reality's data is stored like an infinite hard drive. This isn't science fiction. The math actually checks out thanks to two unlikely clues: black holes and video games. Start with black holes, those cosmic vacuum cleaners. When matter falls in, it doesn't just vanish, it leaves imprints on the event horizon, the point of no return. Stephen Hawking showed these imprints slowly leak back out as radiation, pixel by pixel, like a dying ember glowing with its last bits of heat. Here's the twist: that radiation carries all the information about what fell in, encoded on the black hole's 2D surface. It's as if the universe stores 3D data on a 2D canvas, just like a hologram stores depth on a flat plate. Now enter video game logic. Modern games create vast 3D worlds, but the code running them flat text files. Physicists see the universe similarly. They add S/CFT correspondence, a mathematical bridge between string theory and quantum physics, suggests our 3D cosmos might be rendered from a 2D code written at the edge of space. Picture Minecraft's blocky terrain. What you explore feels three-dimensional, but it's all computed from lines of simpler rules. If true, even your thoughts could be shadows of information flickering on some distant cosmic screen. But why would nature work this way? Efficiency. Storing data in 2D saves space, like compressing a movie to stream it faster. Some theorists argue this explains why the universe has finite information density, why there's a smallest possible pixel of reality, the Planck length. Others wonder if we're holograms, who or what is running the simulation. The answer might be nobody. The holographic principle doesn't require programmers. It's just how space-time could fundamentally operate, with gravity and quantum mechanics stitching the illusion together. Critics point out we've never detected this 2D boundary. It's likely trillions of light years away if it exists. Yet experiments like the holometer at Fermilab hunt for quantum fuzz in spacetime, potential glitches in the cosmic projection. Whether the holographic principle holds or not, it's reshaped physics' biggest questions. After all, if reality is a hologram, then every galaxy, every atom, even you might just be data dancing on the edge of nothingness, a cosmic masterpiece painted with the brush of symmetry itself. Quantum entanglement, that spooky connection Einstein hated, might be the holographic universe's signature trick. Picture two particles born together, then flung to opposite sides of the cosmos. Change one and its twin reacts instantly, faster than light. How the holographic principle whispers an answer: they're not truly separate. Those particles might be threads stitching through a hidden dimension, tied together where the 2D boundary of reality folds in on itself. This wild idea, nicknamed ER=EPR after two landmark physics papers, suggests entanglement and wormholes are two sides of the same cosmic coin. Think of spacetime as a stretched rubber sheet. Poke two holes far apart, then thread a string through them underneath. From above, the holes seem unconnected, but tug the string, and both holes move in sync. That's ER=EPR in action. The string is a wormhole or Einstein-Rosen bridge, threading through a higher dimensional space we can't see, the particles. They're just the visible ends of that invisible thread, their entanglement a shadow of the wormhole's geometry. It's as if the universe cheats by storing their connection outside our 3D reality, on that hypothetical 2D surface where all information lives. Here's where symmetry flexes its muscles. The holographic principle treats information like an indestructible currency. It can't vanish, only transform. When entangled particles interact, their states flip in perfect sync, preserving the total information just like a balanced equation. This isn't magic, it's the universe double-checking its books. Even black holes, those information-gobbling monsters, obey the rules. Hawking radiation carries scrambled data out, ensuring nothing's truly lost, just rewritten in a quantum dialect we're still learning to read. Want a real-world analogy? Try a game of cosmic whack-a-mole. Imagine two moles, your particles popping up randomly in distant holes. They seem independent until you realize their hammers are connected beneath the board by a hidden rod, the wormhole. Every hit on one mole jolts the other, not through speed, but through a shared structure you can't see. That's entanglement without forbidden faster-than-light signals. The action happens offstage in the hologram's 2D code. Critics argue we can't prove these wormholes exist. They're mathematical phantoms, vanishingly small and unstable. Yet experiments with quantum computers have simulated miniature versions, showing entangled qubits behaving as if linked by spacetime tunnels. It's early days, but each clue hints that the universe's love for symmetry runs deeper than shapes or forces. It might be knitting reality together with invisible threads, one entangled stitch at a time. Whether ER equals EPR holds up or not, it's teaching us to think differently about connectivity. Distance might be an illusion, separation a trick of perception. If true, every interaction from a photon hitting your eye to neurons firing in your brain could be echoes of a vast hidden symmetry, a hologram where every pixel is perfectly, profoundly linked. Flip a coin, spin it, reverse its path mid-air. If you could do all three at once, it would land exactly as before. That's the essence of CPT symmetry, the universe's most unbreakable rule. Charge, parity, and time. Together, they form a trifecta so fundamental that if you simultaneously reverse a particle's charge, turning matter into antimatter, mirror its position like flipping a glove inside out, and run the clock backward, the laws of physics must stay perfectly unchanged. It's not just a quirk, it's the cosmic anchor keeping reality consistent. Let's unpack this with a visual. Picture a Feynman diagram, those squiggly lines physicists use to map particle interactions. Normally, an electron and positron, its antimatter twin, annihilate into a photon. Now apply CPT, reverse the charges, positron becomes electron. Flip the diagram like a mirror, left becomes right, and run the animation backward. Astonishingly, you get the same event just viewed through a funhouse mirror of transformations. This symmetry isn't just mathematical elegance, it's baked into quantum field theory so deeply that violating it would unravel the very equations that predict particles' behavior. Why does nature care so much about this triple symmetry? Think of it as reality's ultimate failsafe. Alone, any of these flips can fail. Time reversal, for instance, breaks when particles decay. You can't unscramble an egg. Parity fails in weak nuclear forces where certain particles spin only left-handed. Even charge symmetry stumbles. The Big Bang should have created equal matter and antimatter, yet we live in a cosmos dominated by matter. But combine all three, the universe balks. No known phenomenon violates CPT symmetry, not even black holes or quantum foam. It's the one rule even the cosmos won't bend. Here's where it gets eerie. CPT symmetry suggests antimatter isn't just opposite charged matter. It's matter moving backward in time. Feynman famously visualized positrons as electrons zigzagging into the past. This isn't mere metaphor, the math supports it. In quantum equations, antiparticles behave identically to particles with reversed time, so that positron zipping toward you. From its perspective, you're the one moving backward, your morning coffee unpouring itself into the pot. Experiments at CERN push this to the limit. By trapping antihydrogen, a positron orbiting an antiproton, physicists test if it absorbs light at the exact same frequencies as regular hydrogen. A tiny discrepancy would hint at CPT violation and rewrite physics. So far, the universe passes every test, even the craziest quantum fluctuations, virtual particles blinking in and out of existence, respect CPT balance. What if we could break it? The consequences would be staggering. Causality might crumble, effect preceding cause, memories of futures that never were. The cosmic ledger keeping track of energy and information would glitch. Thankfully, nature seems to have a bulletproof lock on this symmetry. And that's the real wonder. Beneath the chaos of the cosmos, there's an order so precise, so unwavering, that even time itself must bow to it. CPT symmetry isn't just a law, it's the universe's way of insisting that, no matter how you twist it, reality always adds up. CPT symmetry is flawless, yet our universe isn't. That's the haunting contradiction at the heart of cosmology. If matter and antimatter were perfectly balanced at the Big Bang, they should have annihilated each other in a burst of pure energy, leaving behind an empty cosmos. Instead, for every billion antimatter particles, 1,000,001 matter particles survived. That 1 in a billion imbalance is why you exist. It's as if the universe's mirror shattered just slightly, with more glass falling on one side than the other, and we're living in the leftover fragments. So how did symmetry break? One clue hides in neutrinos, those ghostly particles that barely interact with matter. Leptogenesis, a leading theory, suggests ultra-heavy neutrinos in the early universe decayed unevenly, producing more matter than antimatter. Picture a cosmic scale tipping when invisible weights vanish. Except these weights were particles so massive, they made the Higgs boson look puny. Their decays, governed by conditions so extreme they'd vaporize black holes, might have scribbled the first lopsided equations into reality. But why didn't CPT symmetry prevent this? Here's the twist. CPT demands balance, but not in the way you'd expect. It insists the totality of physical laws stays identical under reversal, not every single event. Imagine a film where reversing every frame still makes sense, even if one scene shows a vase shattering while its reverse shows glue assembling the pieces. The overall story stays coherent. Similarly, the universe might have local patches where matter dominates, while somewhere beyond our cosmic horizon, antimatter reigns, balancing the ledger where we can't see it. For a visceral analogy, think of a snow globe shaken violently after the Big Bang. Most snowflakes' particle pairs landed symmetrically, melting into energy. But a precious few flakes caught on microscopic ridges, quantum fluctuations, sticking as matter. Sakharov's conditions, 3 rules any matter-generating mechanism must follow, hint that this required a universe out of thermal equilibrium where particles could feel the arrow of time. It's like cooling molten metal suddenly. Imperfections matter freeze in before symmetry can smooth them out. Experiments like LHCb and neutrino observatories hunt for proof. They've caught electrons and their heavier cousins, muons, behaving differently, a crack in the mirror called CP violation. But it's not enough to explain our matter-rich cosmos. Upgraded colliders might spot rarer particle decays or neutrino oscillations that tilt the scales further. Or perhaps the answer lies in gravitational waves from cosmic strings, frozen defects in spacetime that could have twisted matter's odds during the universe's first trillionth of a second. The deeper truth, CPT symmetry didn't fail. It allowed for pockets of imperfection, knowing they'd cancel out in the multiverse's infinite ledger. We're just lucky enough to inhabit a bubble where symmetry's slight frown meant the difference between nothingness and galaxies. And that's the ultimate cosmic irony. The universe's most unbreakable rule needed to bend just a little for us to be here at all. What if the Big Bang wasn't the beginning, just the latest reboot in an infinite cosmic cycle? Roger Penrose's Conformal Cyclic Cosmology paints this mesmerizing picture where universes don't die but transform, their endings folding seamlessly into new beginnings through a symmetry so profound it bends time and space into a perfect loop. Imagine the heat death of our universe, not as a cold, empty graveyard, but as a blank canvas resetting itself. When all matter evaporates into radiation and black holes dissolve into whispers of energy, something extraordinary happens. The universe becomes scale invariant. Distances lose meaning. A single photon's wavelength stretches to infinity, and suddenly, the infinite future of one eon aligns mathematically with the infinitesimal singularity of the next. Penrose's diagrams, those intricate rubber sheet geometries, show this elegantly. Picture 2 funnels placed tip to tip, each representing an eon. The wide mouth of the first funnel is its Big Bang, the narrow end its heat death. But instead of stopping, the narrow end conformally connects to the next funnel's narrow end, becoming its Big Bang. Conformal symmetry is the magic here. It lets you stretch or compress spacetime like a rubber sheet, preserving angles but not sizes. To the universe, this transformation is irrelevant. It doesn't care if it's infinitely large or infinitely small. Only the shape of events matters, not their scale. Here's where it gets wild. Penrose and his team hunted for evidence in the cosmic microwave background, the afterglow of our Big Bang. They claim to find concentric rings of slightly cooler spots like ripples in a pond. These, they argue, are gravitational wave imprints from supermassive black hole collisions in the previous eon, echoing across the conformal boundary. Skeptics counter that the patterns could be random noise, but if verified, it would mean we're literally seeing shadows of a universe that existed before time as we know it began. Think of it like a phoenix universe. Instead of burning to ash, it sheds all measurable dimensions, becoming an abstract template for the next cycle. No information is lost, just rewritten in a dimensionless language where a galaxy and a grain of sand are mathematically identical. This isn't science fiction, it's a radical reimagining of entropy. Normally, entropy increases, driving chaos, but at the conformal boundary, entropy resets. The universe forgets its own disorder, like a clock striking midnight and erasing all memory of the day before. Could we ever prove this? Maybe. If future telescopes detect more of those eerie rings, or if quantum gravity models reveal how conformal symmetry survives the Big Bang's fury, Penrose's vision might leap from blackboard to textbook. Until then, it stands as a testament to symmetry's power, not just as a property of space or particles, but as the hidden hand that might weave eternity itself, one eon at a time. Hawking points aren't your average cosmic anomalies. They're like ghostly fingerprints left on the universe's oldest light, hints that black holes from a previous cosmos might have screamed their existence into ours. Picture the cosmic microwave background, that faint glow from the infant universe, as a sprawling fresco. Most of it looks smooth, but zoom in, and you'll spot strange, circular patches, slightly cooler regions with sharp edges like celestial bullseyes. Penrose argues these are the echoes of supermassive black holes that evaporated in the eon before ours, their final bursts of Hawking radiation imprinted onto the CMB as faint, ring-shaped scars. How would that even work? Think of it like a sonic boom in reverse. When a black hole fully evaporates, a process taking longer than the current age of our universe, it releases a sudden, intense pulse of energy. In conformal cyclic cosmology, that pulse doesn't vanish. It gets stretched across the conformal boundary between eons, transforming into a spherical ripple in the quantum fields of the newborn universe. By the time our Big Bang ignites, that ripple manifests as a faint temperature dip in the CMB, a fossilized whisper of a long-dead cosmic giant. Detecting these whispers isn't easy. The CMB is already a puzzle of fluctuations with random variations that mimic signals. Penrose and his collaborator, Vark sifted through data from Planck and WMAP satellites using algorithms to filter out noise. Their claimed discovery of concentric rings, some spanning several degrees in the sky, sparked fierce debate. Critics point out similar patterns can emerge from statistical noise, like seeing faces in clouds. But if verified, these rings would be more than just curiosities. They'd be time tags from a pre-Big Bang epoch, hard evidence that our universe is just one link in an endless chain. Here's where it gets even stranger. These Hawking points wouldn't just be random blemishes, they'd follow a distinct distribution. In Penrose's model, the most massive black holes from the previous eon leave the clearest imprints, meaning their ring patterns should cluster in ways that reflect how black holes tend to gather in galactic centers. It's like finding a constellation where the stars aren't just arranged randomly, but mirror the layout of a city from a forgotten civilization. The implications would rewrite cosmology. If Hawking points are real, they'd challenge the inflationary model's prediction of a near-uniform early universe, suggesting instead that some structures are inherited. Suddenly, the CMB isn't just a baby picture of our cosmos, it's a palimpsest with faint traces of a ghost universe bleeding through. Future telescopes, like the proposed CMB S4 project, could settle the debate with ultra-high-resolution maps. If those elusive rings persist, we might finally have a window into the universe's cyclical rhythm, where every ending is a prelude and every Big Bang carries the echoes of a past we're only beginning to hear. Picture a snowflake, but not just any snowflake, one sculpted in 248 dimensions, its crystalline arms branching in directions the human mind can't visualize. That's the E8 Lie group, a mathematical object so symmetrical, so staggeringly complex, it makes the Mandelbrot set look like child's doodle. Surfer physicist Garrett Lissy threw this geometric monster into the physics world with a bombshell claim. E8 might be the hidden scaffolding of reality itself, a master symmetry weaving together every particle and force in existence. Lissy's audacious idea starts with a simple premise: the universe loves patterns. The standard model's particles fit into neat symmetry groups like SU3 for quarks and U1 for electromagnetism, but they're fragmented like pieces from different puzzles. E8, a 248-dimensional shape first mapped in the late 19th century, could be the box art showing how all those pieces interlock. In his groundbreaking 2007 paper, Lissy arranged known particles as points on E8's lattice, with empty slots predicting new particles, like a periodic table where half the elements are still undiscovered. The kicker: gravity slots in naturally, something most unification theories force with mathematical duct tape. Visualizing E8 is like trying to imagine a hypercube with 1,000 faces. Mathematicians project it into 3D using kaleidoscopic animations, points flashing as they rotate through higher dimensions, tracing patterns that briefly resolve into familiar shapes before dissolving again. One mesmerizing projection is the E8 petal, where 8 concentric rings of vertices pulse like a cosmic flower blooming in impossible directions. Hidden in this geometric dance are the symmetries of electrons, neutrinos, even hypothetical gravitons, all unified under a single, elegant structure. But beauty doesn't equal truth. Critics pounced on gaps in Lissy's model. E8 struggles to explain particle masses or the hierarchy problem, why gravity is absurdly weaker than other forces. Some physicists argue it's mathematical poetry without experimental teeth. Others note that E8's rigid symmetry leaves no room for the messy, broken symmetries we observe in nature. Then there's the dimensionality problem. Our universe has 3 spatial dimensions. Where do the other 245 hide? Lissy suggests they're compactified, curled into sizes smaller than quarks, but skeptics call this hand-waving. Yet the theory refuses to die. Recent work shows E8 popping up in unexpected places, from the quantum Hall effect to string theory's hidden algebras, the biggest tantalizing clue. The spin connection in Lissy's model resembles equations for quantum gravity, hinting that space-time itself might emerge from E8's geometry. Future particle colliders could hunt for E8's predicted particles, like the elusive X boson that might mediate proton decay. Whether E8 is the ultimate symmetry or just a breathtaking mirage, it reminds us that the universe's deepest truths might be written in a geometric language we're only beginning to decipher, one where every particle, every force is a note in a 248-dimensional symphony. What if the same geometric perfection that shapes subatomic particles also hides inside your DNA? The E8 symmetry group, that 248-dimensional mathematical marvel, might not just govern quantum fields, it could be lurking in the very building blocks of life. Take the humble virus. Many, like the adenovirus, pack their genetic payloads inside icosahedral capsids, 20-sided protein shells with symmetries so precise they'd make a diamond look crude. Zoom in on these microscopic cages, and you'll find their atomic arrangements mirror fragments of E8's lower dimensional projections, as if nature used the same geometric cheat sheet for both viruses and particle physics. This isn't coincidence, it's optimization. Icosahedral symmetry allows viruses to build robust, space-efficient containers from limited genetic instructions. But here's the twist: these same patterns appear in quasicrystals, those mind-bending materials that ordered atoms in 5-fold symmetrical arrangements once thought impossible. In 2011, Dan Shechtman won the Nobel Prize for discovering them, upending centuries of crystallography. Like E8, quasicrystals exist in a tantalizing middle ground between chaos and perfect order, their atomic tiles never repeating yet never random. Now imagine if DNA's double helix with its golden ratio twists is just another expression of this universal toolkit. Scale up and the echoes grow louder. Galactic filaments, the universe's largest structures, thread through space in a cosmic web shockingly similar to quasicrystal patterns. Simulations show dark matter clustering in configurations that, when sliced mathematically, reveal hints of E8's higher dimensional symmetries. It's as if the universe, from the quantum to the cosmic, keeps returning to the same geometric wells, drawing water from deeper springs than we've yet uncovered. Could E8 be the Rosetta Stone linking biology to cosmology? Some biophysicists speculate that DNA's icosahedral tendencies, visible when molecules coil under stress, are evolutionary holdovers from an era when chemistry obeyed simpler geometric rules. Others see quasicrystals as fossils of a prebiotic world where symmetry templated life's first dances. The boldest idea, these patterns aren't just recurring, they're inevitable. Given enough time and energy, any self-assembling system, from star-forming gases to viral proteins, stumbles toward the same optimal geometries coded into reality's fabric. Critics argue these are superficial resemblances, that snowflakes and spiral galaxies share spirals without shared mechanisms. Yet when algorithms simulating E8 symmetries generate shapes indistinguishable from radiolarian skeletons or carbon-60 molecules, it's hard to ignore the whisper of a deeper connection. Perhaps symmetry isn't just a physical law but a creative force, and E8 is its alphabet writing viruses, crystals, and galaxies alike into the same timeless story. Look closely at a fern leaf. Each frond branches into smaller copies of itself, repeating that pattern down to the tiniest vein. Now pull back, way back, until galaxies look like specks on a cosmic web. Notice anything familiar, the same branching, self-similar shapes appear, as if the universe can't resist drawing with the same stencil across unimaginable scales. This eerie repetition isn't just aesthetic, it hints at a radical idea. What if reality is fundamentally fractal, not smooth and uniform, but infinitely detailed, like a Mandelbrot set where every zoom reveals new layers of complexity? Physicists call this scale symmetry, the notion that physical laws operate identically whether you're observing quarks or quasars. Think of it like a cosmic Russian nesting doll. The forces holding atoms together might mirror the gravity shaping galaxy clusters, just playing out on different stages. Simulations of dark matter reveal this hauntingly well. Run the math, and you'll see tiny density fluctuations in the early universe grow into filamentary structures that look uncannily like neural networks or river deltas. The Laniakea supercluster, our galactic neighborhood, even branches in ways that echo the bronchial tubes in your lungs. But here's where it gets mind-bending. If the universe is truly fractal, there might be no smallest or largest level, just an endless recursion. Imagine zooming into an electron and finding an entire micro-universe, complete with its own stars and civilizations. Then zoom out from our cosmos and discover we're just a speck in some higher being's atom. This isn't just sci-fi, it's a serious hypothesis called cosmological natural selection, where black holes birth new universes with slightly tweaked physics, creating an evolutionary tree of realities. Critics argue that known physics breaks this symmetry. Quantum mechanics dominates the tiny, general relativity, the vast, never the twain shall meet. Yet some theories, like scale relativity, propose that space-time itself might be fractal at quantum scales, with tiny, crumpled dimensions smoothing out into the cosmic landscape we see. Others suggest dark energy could be a scale-symmetric artifact, a shadow of quantum jitter magnified to galactic proportions, the most tantalizing clue. The cosmic microwave background's temperature fluctuations follow a near-perfect fractal distribution like static on an old TV tuned to the channel of creation. Future telescopes like the James Webb might spot even finer patterns, while quantum gravity experiments hunt for fractal spacetime in lab-grown black hole analogs. Whether fractal symmetry holds or not, it challenges our obsession with fundamental scales. Maybe the universe isn't built like an onion with discrete layers, but like a hologram where every zoom reveals not simplicity, but endless, shimmering complexity, a cosmic fingerprint repeating itself across the void. Shrinking down to the Planck scale, a realm so small, a single atom would loom like a galaxy. Spacetime stops behaving like the smooth fabric we know. Instead, it churns into a frothing sea of quantum foam, where virtual particles flicker in and out of existence like bubbles in a boiling pot. But this isn't chaos. Look closer and you'll spot something astonishing. Every fluctuation, every flicker mirrors the same pattern at every scale. It's as if the universe took a single geometric blueprint and stamped it across reality, from the vast cosmic web down to the tiniest quantum tremor. This is the fractal vacuum hypothesis, where spacetime itself might be an endless recursion of self-similar structures. Imagine zooming into a fractal like the Mandelbrot set. No matter how deep you dive, the same swirling shapes reappear, infinitely intricate yet perfectly ordered. Now replace those shapes with quantum fluctuations. At one level, you see the dance of electrons and quarks. Zoom in further, and those particles dissolve into smaller ripples, which themselves fragment into tinier disturbances ad infinitum. The cosmos becomes a hall of mirrors, with every reflection echoing symmetries from the macroscopic to the infinitesimal. What could cause such a thing? Some theories suggest spacetime isn't fundamental but emerges from deeper, discrete building blocks, like pixels on a screen, but with each pixel containing its own miniature universe. Loop quantum gravity, for instance, proposes that space is woven from microscopic loops, their interactions creating a fabric that looks continuous from afar but dissolves into granular foam up close. String theory takes it further, with Calabi-Yau manifolds folding into fractal-like geometries at scales a billion times smaller than quarks. These aren't just mathematical curiosities. They could explain why gravity behaves so differently from other forces. It might be leaking into our dimension from deeper layers of this fractal stack. Visualizing this is like stepping into a surreal dream. Picture diving into a quantum ocean where every drop contains another, tinier ocean, each with its own swirling currents and eddies. The fluctuations aren't random noise, they're harmonics of a deeper symmetry resonating across dimensions. Even black holes might play by these rules. Their event horizons could be fractal membranes, trapping information not on smooth surfaces, but on infinitely crinkled boundaries where every crease holds another universe's worth of data. The implications are dizzying. If spacetime is fractal, then the Big Bang might not have been a singular point but a cascade of nested singularities, like a Russian doll's worth of explosions. Dark energy, perhaps just the cumulative sigh of countless microscopic vacuums bubbling beneath our feet. An entanglement, that spooky connection between particles, might simply be two threads dipping into the same subquantum fractal layer, bypassing our notion of distance entirely. Critics argue this is speculative, and they're right. No experiment has yet probed the Planck scale directly, but hints might lie in unexpected places. Some quantum materials, like graphene, exhibit fractal electron behaviors at room temperature. Cosmic ray collisions could, in principle, expose spacetime's granularity if detectors become sensitive enough. Even the holographic principle, with its 2D boundary encoding 3D reality, feels like a fractal idea in disguise. Whether fractal spacetime is real or just a beautiful metaphor, it challenges our deepest assumptions. The universe might not have a bottom floor, no smallest particle, no final theory. Instead, it could be symmetries all the way down, an infinite mosaic where every piece, no matter how tiny, reflects the whole. And if that's true, then every time you gaze at a snowflake or a galaxy, you're catching a fleeting glimpse of the cosmos's most persistent whisper. Scale is an illusion and pattern is the only law. Most crystals, diamonds, snowflakes, even salt grains, get their beauty from atoms arranged in repeating spatial patterns. But what if a crystal could repeat not just in space but in time? Enter time crystals, the universe's most bizarre stop-motion animation, where quantum systems pulse in perfect, perpetual rhythm without any energy input. Picture a diamond that doesn't just sit glittering on a ring but breathes. Its atomic structure cycling between configurations like a cosmic metronome, ticking forever even at absolute zero. This isn't science fiction. In 2016, Nobel laureate Frank Wilczek's wild theoretical idea became lab reality, revealing a fourth-dimensional symmetry hiding in plain sight. How does something crystallize in time? Normal crystals break spatial symmetry. Their atoms lock into grids that look identical if you shift perspective by certain angles. Time crystals break temporal symmetry, meaning their quantum states repeat at fixed intervals without following the usual rhythm of external forces. Imagine a row of pendulums all swinging at different rates. Now suppose they suddenly sync up, swinging together twice as slowly as your pushes. That's a time crystal, a system that ticks at its own stubborn pace, like a drumbeat resisting the conductor's tempo. The magic lies in discrete time translation symmetry breaking. Normally, physics treats all moments as equal. A lab experiment today should behave like one tomorrow. But time crystals pick favorites, only repeating perfectly after, say, 2 or 3 cycles of the driving force. It's as if you flipped a light switch on, and the bulb responded with a flash pause pattern, locked into a rhythm all its own. This defiance of equilibrium is what makes them revolutionary. They're not perpetual motion machines. They don't create energy, but they do evade the universe's march toward chaos, dancing endlessly in quantum lockstep. Watch a time crystal in action, and you'll see quantum weirdness turned into visible poetry. In a 2017 experiment, researchers trapped 10 ytterbium atoms in a laser grid, nudging them with pulses. Instead of mirroring the laser's rhythm, the atoms began flipping their spins in a cycle twice as long, like a skipped heartbeat stabilizing into its own groove. Even more astonishing, the pattern persisted indefinitely, surviving noise and imperfections that should have disrupted it. This wasn't just stability, it was a new phase of matter, one where time itself becomes a playground for symmetry. What's the deeper secret here? Time crystals hint that nature might encode symmetries not just in stuff, but in rhythms. Some theorists suggest these structures could be fossils from the early universe when time's arrow hadn't yet hardened. Others speculate they might power future quantum computers, with their flawless cycles acting as error-resistant clocks. But the most tantalizing idea: if time crystals can exist, then time might not be the featureless river we assume. It could have textures, hidden folds, and creases where symmetry loops back on itself, offering glimpses into a universe far more structured, far more musical than we ever imagined. The kicker: time crystals don't just exist, they thrive in the most hostile conditions. Chill them to near absolute zero, blast them with disorder, and they keep ticking. It's as if the universe whispered a secret into matter's ear. Equilibrium is optional, and in that whisper, we might just hear the first notes of time's true symphony. If time crystals can dance in the frozen quiet of a lab, what might they be doing in the violent heart of a neutron star? These cosmic extremes where matter crushes into nuclei so dense, a teaspoon weighs as much as a mountain, could be nature's ultimate timekeepers. Picture a pulsar, that lighthouses of the cosmos, beaming radiation with a rhythm so precise it rivals atomic clocks. Now, imagine those pulses aren't just the spin of a star, but the heartbeat of a macroscopic time crystal, its quantum choreography scaled up to stellar proportions. Pulsars already defy intuition. A typical neutron star rotates hundreds of times per second. its magnetic field whipping charged particles into focused beams that sweep past Earth like a cosmic strobe light. But here's the puzzle: some glitch. Their spins speed up or slow down unpredictably, as if something inside is slipping, then catching again. What if that something is a time crystal, a chunk of ultra-dense material locked into its own rhythmic cycle, tugging against the star's rotation? In this scenario, the pulsar isn't just a dead star's corpse. It's a quantum metronome, its ticks driven by symmetries deeper than gravity itself. The math gets wilder. Under pressures near a neutron star's core, quarks might unzip into stranger forms of matter, like up and down quarks reorganizing into a crystalline lattice. Normally, such structures would melt instantly, but if they form a time crystal, their repeating pattern could persist in time, flipping between states with each pulsar rotation. It's like a diamond that doesn't just sit in space but pulses in fourth-dimensional harmony, its atomic bonds echoing to a rhythm set during the star's violent birth. Black holes offer an even darker twist. Near the event horizon, spacetime stretches into infinite thinness, a perfect stage for quantum effects to balloon to macroscopic scales. Theorists like Wilczek suggest that infalling matter could get stuck in time crystal loops, vibrating at the horizon like a drumhead forever reverberating from a single strike. These wouldn't be crystals made of atoms, but of warped spacetime itself, their cycles imprinting on Hawking radiation. Detect a pattern in that fading glow, and you might have proof that even black holes tick to quantum time's secret beat. The implications ripple outward. If cosmic time crystals exist, they could synchronize universal rhythms we've barely noticed. Pulsar timing arrays networks of dead stars used to hunt gravitational waves might already be recording their echoes. Future telescopes tuned to quantum gravity's whispers could spot anomalies, pulsars whose glitches align in fractal patterns, or black holes emitting radiation in unnatural harmonics. Critics argue that isolating a time crystal signal from astrophysical noise is like hearing a single violin in a hurricane. Yet if neutron stars do harbor these structures, they'd be more than curiosities. They'd be relics of symmetry forged in collapse, clocks that kept ticking when the universe itself seemed to stop. And that's the haunting beauty of this idea. Time crystals might not just be in labs or stars, but woven into the fabric of reality, waiting for us to listen to their rhythm. Picture a fishbowl where the water gets thicker and heavier as you swim toward the bottom. Now imagine that fishbowl isn't filled with water. It's filled with spacetime itself, warped so severely that light bends like taffy near the edges. That's anti-de Sitter space, or AD-S for short, a cosmic funhouse where gravity behaves like no place in our observable universe. But here's the twist: the fish inside that bowl, living their entire lives in this distorted reality, might never realize they're actually projections of a flat, gravity-free universe painted on the bowl's surface. This is the spine-tingling promise of AD-S/CFT duality, a theory so revolutionary it redefines where reality truly lives. At its core, AD-S/CFT proposes an exact mathematical mirror. A warped, gravity-filled universe like AD-S is perfectly equivalent to a flat, ordinary universe governed by quantum rules alone, a conformal field theory or CFT. Think of it like a cosmic vending machine. Drop in a black hole in AD-S space and out pops a seething soup of quantum particles on the boundary. Manipulate those particles just right, and you've secretly reshaped the black hole's interior. The two descriptions aren't just similar, they're mathematically identical, like a novel translated into another language without losing a single nuance. Escher's mind-bending art offers a glimpse into how this works. Picture his famous circle limit engravings, where fish shrink as they swim toward the edge, yet never quite reach it. In AD-S space, that edge isn't just an artistic trick. It's the boundary where gravity vanishes and quantum information takes over. Every twist of spacetime inside the bowl corresponds to precise quantum entanglements on the flat surface. A collapsing star in the center, that's just quantum chaos on the rim, rewritten in the language of curvature. This duality doesn't just link gravity and quantum physics. It suggests gravity emerges from quantum information, like 3D shadows cast by 2D data. Why does this matter? Black holes become the ultimate test case. Hawking's paradox that black holes seemingly destroy information melts away if the hole's interior is just a holographic projection. The information isn't lost, it's smeared across the boundary in quantum code. Even wormholes get a makeover. An entangled pair of particles in the CFT might describe a space-time tunnel in the ADS bulk, their quantum connection literally weaving the fabric of geometry. It's as if the universe runs on two operating systems simultaneously, one for gravity, one for quantum fields, and ADS/CFT is the Rosetta Stone that proves they're the same program. Critics argue ADS space is too idealized, our universe is expanding, not warping inward. Yet experiments with quark-gluon plasmas, those ultra-hot soups of particles created in heavy ion colliders, show behavior eerily matching ADS/CFT predictions. It's like finding a fish that somehow remembers living in Escher's bowl, even after you've drained the water. Whether the duality holds in our cosmos or not, it's already reshaped physics' biggest questions, proving that sometimes the deepest truths aren't hidden in the fabric of reality, but in the holographic reflection dancing at its edges. Crossing a black hole's event horizon should be uneventful if Einstein's general relativity holds. You'd float toward oblivion, blissfully unaware of the point of no return, like a salmon drifting downstream toward a waterfall it can't yet see. But what if the moment you cross, you're vaporized by a searing wall of energy? That's the firewall paradox, a cosmic glitch where quantum mechanics and gravity clash so violently, they torch the very symmetries we thought governed reality. Picture this, an astronaut, let's call her Rita, plunges toward a black hole. According to relativity, space-time near the horizon is smooth if stretched, a gentle slope into darkness. But quantum mechanics whispers a darker tale. As Rita falls, her particles entangle with Hawking radiation leaking from the hole. Here's the rub. Quantum rules say entanglement can't be cloned, yet relativity insists Rita's information must survive inside. The only escape, a fiery discontinuity, a firewall that burns away the excess quantum links, annihilating Rita in an instant. ADS/CFT duality cranks the paradox to 11. Remember that cosmic fishbowl. On the boundary, the CFT describes Rita's fate as a scrambling of quantum information, messy but lawful. But inside the ADS bulk, her smooth journey smacks into the firewall's brutality. The duality insists both stories are true, meaning the same physics that stitches space-time together also demands a lethal discontinuity at its seams. It's as if the universe coded a failsafe. When symmetries strain too far, reality snaps like an overstretched rubber band, trading elegance for sheer, fiery consistency. Now animate Rita's last moments in two flavors. Version 1. She crosses the horizon unharmed, her clock slowing to a crawl from an outsider's view, her body spaghettifying gently in the dark. Version 2. A plank-length thick inferno, hotter than supernova, shreds every atom of her into scrambled Hawking radiation. Both outcomes stem from impeccable math, a cosmic schism where the rules can't agree on whether the horizon is a curtain or a crematorium. The stakes: firewalls don't just kill astronauts, they kill equivalents, the principle that free fall feels like weightlessness. If horizons burn, Einstein's happiest thought crumbles. Yet some theorists argue firewalls are illusions, artifacts of misapplied quantum rules. Others suggest they're real but rare, triggered only by specific quantum states. A third camp, the truth lies in between, a fuzzball horizon where strings tangle into a quantum froth, neither smooth nor fiery, but something stranger. Experiments are understandably scarce, but clues might hide in analog black holes lab setups using sound waves or ultra-cold atoms to mimic event horizons. Already, these analogs show particles appearing where horizons should be, like spectral echoes of firewalls. Meanwhile, precision measurements of old Hawking radiation could reveal telltale scars of past infernos. Whether firewalls exist or not, their terror has purpose. They're the universe's way of reminding us, somewhere beyond the horizon, our dearest symmetries break and new, fiercer laws take hold. And in that breaking, we might finally glimpse the true architecture of reality, not smooth, not orderly, but forged in the quantum fires where space-time itself is born. Numbers we use every day, 1, 2, 3, live on a simple number line. But what if the deepest secrets of the universe aren't written in these familiar digits, but in an 8-dimensional numerical alien language where multiplying 7 by 6 can give different answers depending on the order you do it? Meet octonions, the wildest number system in mathematics, a swirling, 8-dimensional web that might just be the hidden code behind quarks, electrons, and all the fundamental particles. At first glance, octonions look like someone took complex numbers, those with imaginary eyes, and cranked them up to cosmic absurdity. Where complex numbers have one imaginary dimension, and quaternions, their 4-dimensional cousins, power your smartphone's gyroscope, octonions explode into 8. Picture a hyperspherical labyrinth with 7 imaginary directions, each labeled with its own quirky symbol I, J, K, L, M, N, O, plus our humble real numbers. But here's where things get weird. Multiply I by J and you get K, but reverse it. J times I gives negative K. And it gets worse, the order matters so much that I times J times L isn't the same as I times J times L. This non-associative property makes octonions the mathematical equivalent of a Rubik's Cube that reshuffles itself every time you blink. Yet this very strangeness might be why octonions whisper to particle physics. The standard model's menagerie of particles fits suspiciously well into octonion symmetries. Take the 8 gluons that mediate the strong force. Their interactions mirror octonion multiplication tables. The 6 quarks and leptons, they slot into octonion geometries like puzzle pieces, with their charges and spins tracing patterns across those 8 dimensions. Even the Higgs field finds a natural home here, as though octonions were scaffolding the universe built its laws upon. Visualizing this is like trying to sketch an 8-dimensional symphony. Mathematicians project octonions into 3D using the phonoplane, a star-shaped diagram where each line represents a multiplication rule. Picture 7 points connected in loops, with arrows dictating how terms flip signs when multiplied. It's less a rigid structure than a living thing, where numbers dance around each other in an intricate ballet of pluses and minuses. But why would nature use such an arcane system? Some theorists argue that octonions' non-associativity isn't a bug, it's the feature. Just as quantum uncertainty introduces fundamental unpredictability, octonions might encode a built-in flexibility that lets particles morph between states. Others speculate that octonions describe symmetries hidden at energies so high, they'd make the Large Hadron Collider look like a toy. At these scales, spacetime itself might unravel into octonionic threads, weaving particles from numerical vibrations. Critics pounce on the obvious problem. If octonions are so fundamental, why don't we see their fingerprints everywhere? The answer might lie in their fragility. The moment you try to build familiar physics from octonions, their non-associative tendrils start tangling equations. It's like trying to build a house from jelly, beautiful in theory, messy in practice. Yet string theory flirtations with octonionic calobi, Yau manifolds and sporadic groups, those mathematical oddities like the monster group, suggest they're not just ghosts. The boldest idea, octonions might be the language of pre-geometry, a realm before space and time, where pure math writes the rules particles later obey. If true, then every electron, every photon, is a shadow of an 8-dimensional symphony we're only beginning to hear. And that's the octonion enigma. The numbers that break every rule might be the ones holding reality together. If octonions seem like mathematical oddities, wait until you see where they might actually live. The twisted, six-dimensional shapes hiding inside string theory's 10-dimensional playground. Picture our universe not as the familiar 3 dimensions of space and 1 of time, but as a 10-dimensional beast where the extra 6 dimensions curl up into intricate geometries called Calabi-Yau manifolds. These shapes aren't just random squiggles, they're hyperdimensional sculptures where octonion symmetries might literally shape the fabric of reality. Take one of these Calabi-Yau spaces, a knotted, honeycombed structure smaller than a quark, and imagine it vibrating. Each vibration mode corresponds to a particle in our 4D world: electrons, quarks, even the Higgs boson. Now here's the kicker: the symmetries governing those vibrations aren't just similar to octonions, they're built from them. The way strings wiggle through these folds mirrors how octonions multiply, their non-associative dance imprinting on the particles we observe. It's as if the universe took an 8-dimensional numerical system and projected it onto 6-dimensional geometry, leaving behind shadows we recognize as matter and forces. Why would nature choose something so convoluted? Because octonions are exceptional, literally. In mathematics, there are only 5 exceptional Lie groups, symmetry families so rare and beautiful they stand apart from infinite ordinary ones. The largest, E8, is deeply tied to octonions, and guess what? E8 also emerges naturally in string theory's equations when you stretch them to their breaking point. This isn't coincidence, it's a hint that the universe might prefer esoteric math for its foundational blueprints. Zoom in on a Calabi-Yau manifold surface, and you'll find it studded with tiny, octonion-shaped grooves. When strings loop around these grooves, their winding numbers determine particle properties like charge and spin. An electron's negative charge, that could be a string wrapped 3 times around an octonion-respecting cycle. A quark's color charge may be a string vibrating in a specific octonion harmonic. Even the messiness of the standard model, its 3 generations of particles, its seemingly random masses, might just be the fallout of how octonions fracture when crammed into these compact spaces. Critics argue this is mathematical wishful thinking, that just because octonions fit doesn't mean they're real. But consider this: when physicists try to derive particle physics from string theory without octonions, they hit walls. The math gets clunky, requiring endless tweaks. Yet introduce octonion symmetries and equations suddenly snap into place, as if dusting off a corrupted file to reveal a pristine image beneath. It's like finding a key that effortlessly unlocks multiple doors in a labyrinth. The boldest claim: octonions might explain why our universe has this particular set of forces and particles. In the landscape of possible string theory solutions, Calabi-Yau shapes with octonionic symmetries could be special islands of stability, places where quantum fluctuations don't rip spacetime apart. If true, then the reason we live in a universe with electrons, photons, and gravity isn't random chance. It's because octonions carved out a habitable niche in the multiverse's chaos. Whether octonions are ultimately the answer or just another dead end, their presence in string theory is a siren call to physicists. The universe's deepest truths might not just be stranger than we imagine, but stranger than we can imagine, written in a numerical dialect we're still learning to speak. And if we ever crack that code, we might find that the cosmos was never built on simple arithmetic, but on the wild, 8-dimensional melodies of octonions. Galaxies aren't just drifting apart in the cosmic expansion, some are racing in the same direction, like leaves caught in a hidden river. This eerie phenomenon, called dark flow, defies everything we know about the universe's structure. Imagine throwing confetti in the air, only to watch half of it inexplicably surge toward a single point beyond the horizon. That's what astronomers saw when they mapped the motion of thousands of galaxy clusters. A mysterious tug pulling them toward a patch of sky near the constellations Centaurus and Vela. But here's the real shocker: that direction aligns with a faint, controversial axis in the cosmic microwave background, the so-called dark axis. It's as if the universe itself has a preferred direction, a cosmic north pointing to something outside our observable bubble. What could exert such a pull? The leading theory is as unsettling as it is thrilling. A pre-Big Bang structure. Picture our universe as a bubble among bubbles in an infinite multiverse. If another bubble universe grazed ours long ago, its gravitational imprint might still be yanking galaxies toward it, like a ship's wake disturbing the water long after it's passed. Alternatively, it could be a cosmic defect, a frozen crack in space-time from the universe's violent birth, warping the fabric of reality on scales we can barely fathom. Either way, dark flow hints that our universe isn't just shaped by its own history, but by something beyond it. The maps tell the story. Heat-sensitive telescopes like Planck and WMAP revealed the CMB's temperature fluctuations aren't perfectly random. They skew slightly along an axis, a whisper of asymmetry in the afterglow of creation. When astronomers overlaid galaxy cluster velocities, the arrows didn't point outward evenly, they veered toward the same dark axis, as if drawn by a phantom hand. Some clusters move at speeds exceeding 600 miles per second, far faster than cosmic expansion alone can explain. It's like standing in a crowd where everyone suddenly turns to stare at something you can't see. Skeptics argue it's a statistical fluke or a calibration error. After all, dark flow's signal is subtle, buried in noise, but the more data we collect, the harder it is to dismiss. If confirmed, its implications are staggering. The observable universe spans 93 billion light-years, yet dark flow's source must lie farther, meaning it originates from a region so distant, its light hasn't had time to reach us since the Big Bang. This isn't just a mystery, it's a crack in the ceiling of cosmology, offering a glimpse of whatever lies past the edges of our cosmic map. Could dark flow be the first hint of a sibling universe, or the gravitational scar of a collision between cosmic membranes in string theory's brain-world scenario? Until we have answers, it remains one of astronomy's most tantalizing enigmas, a silent river flowing through the cosmos, carrying galaxies toward a destination we may never see. But one thing's certain, if the universe has a hidden compass, its needle is pointing somewhere very strange. Multiversal sibling or cosmic ghost, if dark flow is real, and that's still a fiery debate, it's not just tugging galaxies. It's yanking open the door to one of physics' wildest ideas, that our universe isn't alone, but jostling against others in an invisible higher dimensional sea. Picture a foam of soap bubbles floating in air, each bubble a self-contained universe with its own physics, its own Big Bang. Now imagine two bubbles grazing past each other. Though their surfaces never truly touch, their close encounter sends ripples through the thin walls separating them, ripples that, in our universe, might manifest as that inexplicable pull on distant galaxy clusters. This isn't just poetic speculation. Simulations of bubble universes colliding in the bulk, the theoretical higher dimensional space between worlds, show eerie parallels to dark flow's signature. When researchers at Tufts University modeled such collisions, they found the gravitational aftermath could imprint a preferred direction on one of the bubbles, exactly the kind of cosmic anisotropy we're detecting. It's like finding a fingerprint on a window pane, suggesting something pressed against the other side. The math gets even stranger when you account for the dark axis alignment. If another universe's gravity is leaking into ours, it wouldn't pull uniformly. It'd create a tidal force stretching space-time along a specific vector. That's precisely what we see, galaxy clusters racing toward Centaurus as if surfing a gravitational wave from beyond our cosmic horizon. But how could another universe's gravity reach us? Einstein's equations normally forbid forces crossing between universes unless they're threaded through extra dimensions. String theory's brain-world scenario offers a spine-tingling solution. Imagine our universe as a four-dimensional membrane or brain floating in a higher dimensional bulk, A neighboring brane, another universe, could warp the bulk's geometry, subtly bending our brain like a mattress sagging under a hidden weight. That distortion would tug on everything inside our universe, creating dark flow without any direct matter exchange. It's gravity without borders, a secret handshake between realms we can't see. Critics counter with Occam's razor. Why invoke alien universes when local explanations might suffice? Maybe dark flow is just a statistical fluke, or an artifact of uneven cosmic expansion we don't yet understand. Yet the persistence of the signal across multiple datasets and its alignment with the CMB's dark axis makes coincidence harder to swallow. Others suggest a humbler culprit, a supervoid, a vast underdense region of space pulling galaxies toward it like water draining from a tub. But supervoids large enough to explain dark flow would defy our models of structure formation. The universe shouldn't have gaps that big, the boldest implication. If dark flow confirms a multiverse, it rewrites cosmology's rules. No longer is our universe an isolated accident. It's part of a frothing metacosmos where bubbles collide, merge, and birth new physics in their wakes. Future telescopes like the Euclid satellite could settle the debate by mapping galaxy motions with unprecedented precision. If the flow strengthens with distance, as external gravity would predict, it's game over for the lone universe hypothesis. Until then, dark flow remains a riddle wrapped in a mystery, a cosmic current with no visible source. Whether it's proof of parallel worlds or just a glitch in our maps, one thing's clear. The universe still has secrets tucked in its farthest corners, and some of them might be pulling us toward revelations we're not yet ready to face. Einstein called it spooky action at a distance, two particles separated by light years, somehow mirroring each other's states instantly. But what if that spookiness isn't action at all? What if those particles were never truly apart to begin with? Enter ER equals EPR, the radical idea that quantum entanglement and wormholes are two faces of the same cosmic coin. Picture two black holes born from the same collapsing star. Einstein's equations show their singularities could be linked by an Einstein-Rosen bridge, a wormhole threading through higher dimensions like a needle-pulling spacetime taut between 2 points. Now shrink that wormhole to the size of a quark, and suddenly you've got the perfect shortcut for entangled particles to communicate without breaking the speed of light. The math behind this is mind-bendingly elegant. In one corner, you've got the EPR paradox Einstein and his colleagues pointing out that quantum mechanics demands entangled particles share a connection deeper than locality allows. In the other corner, the ER bridge a geometric tunnel through spacetime's fabric. At first glance, they seem unrelated. But when you feed quantum information into general relativity's equations, something miraculous happens. The wormhole's throat behaves exactly like an entangled pair's quantum link. It's as if spacetime itself is performing a magic trick, folding distant points together so tightly that what looks like two separate particles is actually one quantum entity stretched across the universe. Visualizing this is like playing with funhouse mirrors. Take two entangled electrons. Normally, we draw them as separate dots with a mysterious line connecting them. Now, imagine that line isn't just symbolic, it's a physical wormhole, a Planck-scale tunnel warping through extra dimensions. When one electron spins up, the other spins down not because of some invisible signal, but because they're opposite ends of the same microscopic loop. The wormhole isn't traversable by anything larger than quantum information. You couldn't send a spaceship through it, but for particles, it's a backdoor woven into spacetime's very stitches. The implications rewrite physics rulebook. Suddenly, entanglement isn't a paradox, it's geometry. Black holes swallowing entangled particles, they're just feeding information into the wormhole network. The firewall debate. If ER equals EPR, there's no need for a lethal horizon. The particles' connection smooths out the paradox. Even Hawking radiation gets a makeover. Evaporating black holes might release their secrets not as scrambled noise, but as perfectly preserved data streaming through these space-time threads. Experiments are already teasing at this idea. Quantum computers manipulating entangled qubits have simulated wormhole dynamics, showing information echoing between particles as if traversing a tunnel. Meanwhile, tabletop experiments with graphene sheets where electrons behave like relativistic particles have observed emergent wormhole-like correlations. It's still early days, but each hint suggests space-time and quantum weirdness might be dialects of the same deeper language. So next time you hear about spooky action, remember, the universe might not be playing tricks. It's just showing us the hidden stitches in its fabric, wormholes so tiny, so fleeting, that all of reality could be a tapestry woven from their threads. And if that's true, then every entangled particle, every quantum connection, is a whisper from a dimension where distance is an illusion, and separateness is the grandest illusion of all. Quantum teleportation isn't just sci-fi fantasy. It might be the universe's built-in cheat code, written into the fabric of space-time itself through wormholes. Imagine stepping into a shimmering portal like a stargate, not to be torn apart atom by atom, but to have your quantum information flawlessly transmitted through an Einstein-Rosen bridge, reassembling you light years away in the blink of an eye. This isn't the plot of a blockbuster movie, it's the stunning implication of ER equals EPR, where entanglement and wormholes merge into a single phenomenon. Here's how it could work. Take two entangled particles, the quantum equivalent of a cosmic walkie-talkie pair. According to ER equals EPR, these particles aren't just mysteriously linked. They're physically connected by a microscopic wormhole, a Planck-scale tunnel woven into space-time's hidden geometry. Now, introduce a third particle carrying the quantum information you want to teleport, say, the spin state of an electron. By performing a precise quantum operation called a Bell measurement on one of the entangled particles and the target particle, you effectively open the wormhole, threading the information through it. The result, the quantum state vanishes from your location and reappears instantaneously in the distant entangled partner, as if hopping through a backdoor in reality's code. Visualize this with a sci-fi twist, a futuristic teleportation pad where the operator doesn't disintegrate you, but instead manipulates a control panel of qubits, their measurements acting like a key that unlocks the wormhole's gate. The pad itself would be studded with superconducting circuits or ion traps, real-world quantum devices already capable of entanglement. As the operator initiates the sequence, the information encoding your molecular structure would ripple through the wormhole's throat, emerging light years away to reconstruct you perfectly, right down to the last quantum detail. It's not physical travel, but information transfer so precise it mimics travel, like emailing your consciousness across the cosmos. But before you pack your bags for Alpha Centauri, there's a catch. The wormholes predicted by ER equals EPR are unimaginably tiny, far smaller than an atom, and they snap shut the moment you try to send anything more substantial than quantum data. Traversing them physically would require exotic matter with negative energy to prop them open, a substance we've never observed. Even then, the energy costs would dwarf entire galaxies. That's why the universe seems to reserve this trick for particles. Quantum teleportation has already been demonstrated in labs over hundreds of kilometers, but scaling it to humans would demand technologies indistinguishable from magic. Yet the math holds tantalizing possibilities. Recent experiments with quantum computers have simulated wormhole dynamics, showing information traversing what behaves like a microscopic bridge between qubits. In 2022, researchers at Caltech even observed signatures of wormhole-like behavior in a Sycamore processor, a digital approximation of spacetime's hidden plumbing. These aren't real wormholes, of course, but they prove the equations of ER equals EPR describe something real, something the universe might be doing all around us at scales we're only beginning to probe. The most audacious implication: if entanglement is wormholes in disguise, then the entire cosmos might be crisscrossed with these invisible threads, a vast subquantum network connecting every particle that's ever interacted. Teleportation wouldn't be an exception, it'd just be tapping into the universe's default setting. So while human teleportation pads remain fantasy, the particles composing you are already playing the game, whispering to each other through spacetime's secret tunnels. And that's the real magic. The universe might not just allow teleportation, it could be built from it. Feynman diagrams have been the go-to tool for particle physics for decades, those squiggly lines showing particles colliding, annihilating, and transforming like characters in a cosmic comic strip. But what if all those messy diagrams are just shadows of something deeper? Enter the amplituhedron, a jewel-like geometric object so radically simple, it strips away the complexity of particle interactions to reveal pure symmetry at their core. Picture a multifaceted gem floating in abstract space, its glittering surfaces encoding the probabilities of particle collisions without a single reference to spacetime or causality. This isn't just a new way to calculate, it's a revelation that the universe might think in shapes, not stories. The amplituhedron was born from a frustrating puzzle. Calculating how particles scatter after high-energy collisions using Feynman diagrams requires summing thousands, sometimes millions of possible interaction paths. It's like predicting every possible route a leaf might take down a raging river, accounting for every eddy and whirlpool. But in 2013, physicists Nima Arkani-Hamed and Jaroslav Tirankeye discovered something astonishing. Those endless calculations could be replaced by finding the volume of a single, higher-dimensional shape. The amplituhedron's volume isn't measured in cubic meters, but in mathematical terms corresponding directly to collision probabilities. Rotate this shape in just the right way, and its geometry spits out the answer without ever mentioning particles moving through space or time. How does it work? Imagine the amplituhedron as a cosmic die, but instead of numbers, its faces are inscribed with the fundamental rules of quantum field theory. Each facet represents a constraint on how particles can interact, like the edges of a puzzle box guiding where pieces fit. When particles collide, their possible outcomes map to points inside this shape. The volume swept out by those points isn't just proportional to the probability, it is the probability distilled into pure geometry. Even mind-bending quantum effects like virtual particles and loop corrections emerge naturally from the amplituhedron structure, no Feynman diagrams required. The real shocker, the amplituhedron suggests spacetime and locality. The idea that particles interact only when they're close might be illusions. In Feynman's framework, particles travel through spacetime, influencing each other via forces. But the amplituhedron calculates the same results without referencing distances or times. It's as if the universe keeps a secret ledger where interactions are predetermined by an overarching geometric truth, and what we perceive as cause and effect is just a clumsy translation. This aligns eerily with hints from quantum gravity that spacetime isn't fundamental but emergent, like the 3D illusion of a hologram projected from a 2D surface. Critics argue the amplituhedron so far only applies to a simplified version of quantum field theory called planar n equals 4 super Young-Mills, a toy model with extra symmetries real particles lack. Yet its very existence hints that our universe's messier physics might just be a tarnished reflection of this purer mathematical reality. Future extensions could crack open problems like quark confinement or even quantum gravity, revealing deeper symmetries beneath the noise. What's most poetic is the amplituhedron's aesthetic. It's not some chaotic blob but a structure of breathtaking order, where complexity emerges from simplicity like snowflakes crystallizing from vapor. If the universe truly computes particle interactions this way, then beneath the frenzy of quantum fields lies a silent, geometric heart, a master shape whispering that chaos is just symmetry we haven't learned to see. The amplituhedron doesn't just simplify calculations, it obliterates the very stage we thought physics was performed on. If this geometric gem can predict particle collisions without referencing spacetime, what does that say about reality's true foundation? Picture a cosmic puppet show where the puppets move convincingly, but the strings aren't attached to anything tangible. The amplituhedron suggests spacetime might be those illusory strings, while the real drama plays out in a realm of pure mathematical relations, a place where particles aren't things but vertices in an abstract tapestry of symmetry. Let's animate this radical vision. Imagine zooming into a particle collision, not as billiard balls smashing in empty space, but as a shimmering network of connections flexing and reforming. Each particle dissolves into a node, its properties defined not by position or momentum, but by its relationship to every other node. The collision itself becomes a dance of geometric transformations, where probabilities emerge from the angles between vertices, not forces acting across distances. It's as if the universe's source code runs on a graph theory engine, and spacetime is just the user interface our brains evolved to navigate it. This isn't just abstraction, it's a potential solution to physics' biggest headaches. Quantum gravity's central conflict marrying smooth spacetime with granular quantum effects melts away if both are secondary to a deeper structure. Even entanglement's spookiness gains clarity. Particles correlated across light years aren't communicating, they're simply reflections of the same immutable geometric truth. The amplituhedron's silence on locality and causality isn't a bug, it's a feature, hinting that these concepts are emergent like temperature is to molecular motion. Critics argue this pre-geometric view is untestable, a beautiful metaphor with no experimental hooks, yet glimmers of validation appear in unexpected places. Quantum error-correcting codes, the backbone of quantum computing, use similar geometric structures to protect information, as if engineers stumbled onto nature's own redundancy protocols. Meanwhile, simulations of quantum black holes show entropy calculations mirroring amplituhedron-like volumes, suggesting black holes might be natural amplifiers of this deeper reality. Perhaps the most mind-bending implication is existential. If spacetime is derivative, then our perception of a coherent, continuous universe is an evolutionary convenience, a dashboard simplified for survival. The amplituhedron whispers that reality's raw data is a storm of relations, and what we call physics is just our imperfect translation of its flawless geometry. Future theories might not describe how particles move through space, but how space itself crystallizes from something far stranger, a cosmic symmetry so profound, even time is just another emergent shadow. If the universe played fair, matter and antimatter should have cancelled each other out in a burst of pure energy shortly after the Big Bang, leaving behind an empty, lifeless void. Yet here we are, a cosmos teeming with galaxies, stars and planets made almost entirely of matter. This baffling imbalance, known as Barrian asymmetry, is one of physics' greatest unsolved puzzles. Why does anything exist at all? The answer might lie in three revolutionary criteria proposed by Russian physicist Andrei Sakharov, conditions that turned our understanding of symmetry on its head. First, Sakharov declared the universe must have started in a state of Barrian number violation. Normally, processes like proton decay, if it occurs, barely tweak the matter-antimatter ledger. But in the searing heat of the early cosmos, hypothetical particles like X-bosons might have skewed the balance, decaying more often into quarks than antiquarks. Picture a cosmic coin flip rigged by physics. For every billion antimatter particles annihilated, 1,000,001 matter particles survived. That 1 in a billion excess is all it took to seed everything we see today. Next, Sakharov invoked CP violation, the idea that antimatter doesn't just mirror matter, but behaves slightly differently. This isn't just theory, we've caught it in action. Watch a kaon decay, and you'll see its antimatter counterpart disintegrate at a subtly altered rate. like a left-handed pitcher throwing faster than their right-handed twin. Animations of these decays reveal eerie asymmetries, matter particles twirling with a bias that antimatter can't match. Over time, these tiny deviations snowballed, tilting the cosmic scales toward matter dominance. The final ingredient, a departure from thermal equilibrium. In the frenzied expansion of the early universe, matter-generating reactions had to outpace the homogenizing pull of equilibrium, freezing in the asymmetry before nature could correct it. Think of it like supercooling water so suddenly that bubbles get trapped in ice, the universe's freeze-preserved matter's slim lead. Electroweak phase transitions, where the Higgs field switched on like a cosmic breaker, might have provided just such a moment, locking in the imbalance like a snapshot of a spinning coin. Critics argue Sakharov's conditions still can't explain the scale of our matter-dominated reality. Experiments at CERN and neutrino observatories hunt for additional CP violations, while theories like leptogenesis propose ultra-heavy neutrinos as the ultimate symmetry breakers. Whatever the mechanism, baryon asymmetry isn't just a quirk. It's the reason we exist, and that's the ultimate cosmic irony. For life to emerge, the universe had to break its own rules, favoring matter just enough to leave behind a world where atoms, stars, and curious minds could one day wonder why. Neutrinos might be the universe's ultimate sleight of hand, artists' particles so elusive. They could be hiding the secret to why matter won the cosmic lottery. Unlike electrons or quarks, neutrinos come in two potential flavors of existence, Dirac or Majorana. Dirac neutrinos, like most particles, have distinct antimatter counterparts like a left-handed glove and a right-handed glove that can never perfectly overlap. But Majorana neutrinos, they're their own antimatter twins, flipping between matter and antimatter states like a coin spinning so fast you can't tell heads from tails. If neutrinos are Majorana, that self-annihilating duality could have tipped the scales in matter's favor during the universe's first fiery moments. Picture the early cosmos as a roiling soup of particles and antiparticles, constantly colliding and annihilating. Most particles obey strict rules. Electrons annihilate with positrons, quarks with antiquarks, but Majorana neutrinos, they'd have a wildcard ability. Two neutrinos could collide and erase each other's identities, vanishing without requiring an antimatter partner. Now add a dash of CP violation. The same quirk that makes kaon decays asymmetrical, and suddenly, Majorana neutrinos could decay slightly more often into matter than antimatter. Over time, even a 1 in a billion preference would snowball, leaving behind the surplus of protons, neutrons, and electrons that built everything we see. Detecting this neutrino magic isn't easy. If neutrinos are Majorana, they should occasionally trigger a vanishingly rare event called neutrinoless double beta decay, where two neutrons in an atomic nucleus simultaneously transform into protons, emitting only electrons and no antineutrinos. Experiments like Germany's JERDA or Japan's CAM-LAND Zen hunt for this ghostly signature by monitoring vats of purified isotopes, waiting for a flicker of energy that betrays the neutrino's secret identity. Imagine a room filled with mousetraps, each rigged to snap only if a mouse doesn't squeak as it steals the cheese. That's the level of silent precision these detectors need. But here's where it gets twisty. Some theories suggest neutrinos might not be purely Majorana or Dirac. They could oscillate between both states, like a cosmic undercover agent switching identities. Enter sterile neutrinos, hypothetical shadow particles that don't interact with matter at all except through gravity. Detectors like Fermilab's Mini Buoy have spotted anomalies in neutrino oscillation patterns, hints that sterile neutrinos might exist, dancing briefly into reality before vanishing again. If true, these phantoms could be the key to why Majorana behavior emerges at all. Their chiral oscillations tweaking the symmetry, breaking math in ways we're only beginning to model. The implications are staggering. If neutrinos broke the universe's symmetry, they didn't just make atoms possible, they fine-tuned the conditions for life. Too much asymmetry and matter would have clumped into black holes, too little, and everything would have annihilated into radiation. Neutrinos might be the Goldilocks particle, their subtle imbalance threading the needle between chaos and nothingness. And if we ever catch them in the act through a flicker in a detector, a whisper in the data, it'll be proof that the cosmos cheated just a little to make sure we'd be here to notice. Black holes were supposed to be the universe's ultimate shredders, cosmic prisons where information went to die, locked behind event horizons so absolute not even light could escape. That was the grim picture until 1974, when Stephen Hawking dropped a bombshell. Black holes aren't eternal. They slowly leak energy, evaporating over eons through what we now call Hawking radiation. But this elegant solution came with a devastating catch. If a black hole vanishes, what happens to all the information it swallowed? Stars, planets, even entire civilizations reduced to featureless thermal static. That's the black hole information paradox, a crisis striking at the heart of physics' most sacred symmetry, quantum unitarity. Think of unitarity as the universe's ironclad accounting system. In quantum mechanics, information can't just vanish. It can change form, scramble beyond recognition, but it must always be preserved like energy in a closed loop. Now imagine throwing a library into a fire. The books burn to ash, but in principle, every sentence could be reconstructed from the smoke's molecules, the heat's radiation patterns. But toss that library into a black hole, and Hawking's math suggested a far bleaker outcome. The radiation leaking out would be completely random, carrying no imprint of what fell in. It's like burning those encyclopedias and discovering the ashes bear no relation to the original text, as if the universe's ledger had pages ripped out. This isn't just about lost data, it's a threat to reality's consistency. If black holes destroy information, then quantum states aren't just scrambled, they're erased. Unitarity cracks, and with it, our ability to predict anything at all. Physics becomes a coin flip where yesterday's results don't constrain tomorrow's. The paradox ignited a decades-long war of ideas, with Hawking initially betting information was lost, while rivals like Leonard Susskind shouted heresy. The stakes, whether the universe plays by rational rules or capriciously burns its own history. Enter the firewall debate, a desperate scramble to salvage symmetry. If information must escape a black hole, maybe it doesn't wait for evaporation, maybe it smears across the event horizon in a searing Planck energy wall, incinerating anything that crosses. Firewalls would enforce unitarity violently, ensuring data gets encoded in the Hawking radiation, but at a ghastly cost. Einstein's smooth spacetime would shatter at the horizon, replaced by a lethal discontinuity. It's the universe's twisted compromise: preserve quantum rules by torching the very fabric of general relativity. Critics recoiled. Firewalls seemed ad hoc, like gluing a fake gem onto a crown to hide a missing jewel. Why would nature resort to such extremes? Alternatives bloomed. Holographic principles where information paints the horizon's surface, or ER equals EPR's wormholes weaving entangled threads into spacetime seams. Yet each fix dances around the core enigma: how to reconcile the cold determinism of quantum mechanics with the voracious chaos of black holes. Recent breakthroughs tilt toward optimism. Hawking himself reversed course in 2004, conceding information likely escapes, albeit in ways we barely grasp. Simulations of quantum hair suggest black holes might subtly encode data in their gravitational fields, like faint fingerprints on an otherwise smooth sphere. Even firewalls have evolved, with some models suggesting they're selective, flaring only when information risks being lost. The deeper truth: this paradox isn't just about black holes, it's a stress test for reality's architecture. However it's resolved, one thing's clear: the universe guards its symmetries fiercely, even if it takes a firewall's fury or a wormhole's weave to keep them intact. And in that struggle, we're not just spectators, we're detectives piecing together the cosmos's most guarded secret, how to destroy everything yet lose nothing at all. Firewalls aren't the only way to rescue information from black holes. String theory offers a far stranger escape hatch, where the event horizon isn't a smooth, empty gate to oblivion, but a writhing, tangled mass of cosmic spaghetti. Meet the fuzzball, a radical reimagining of black holes not as vacuum cleaners with singularities, but as gigantic knots of strings too jumbled to collapse into a point. Picture a black hole not as a dark, featureless pit, but as a seething ball of yarn where every thread is a vibrating string from string theory's playbook, twisted and coiled into a quantum frenzy. The moment you cross the horizon, you wouldn't hit a firewall, you'd dissolve into the fuzz, your atoms unraveling into the same vibrating strands that make up the black hole itself. No singularity, no lost information, just one big, fuzzy cosmic loom weaving everything into its fabric. This wild idea comes straight from string theory's toolbox. Normally, strings, those tiny, oscillating filaments that replace particles in the theory, are too small to see, dancing in dimensions curled up tighter than a proton. But in a black hole, the sheer density of mass and energy might stretch them to macroscopic scales, puffing up the horizon into a fuzzy, stringy surface. Think of it like stuffing a million guitar strings into a basketball. They can't all collapse to a point, so they fill the space, vibrating at different frequencies like a cosmic chord that encodes every bit of information that ever fell in. What's mind-blowing is how this solves the information paradox. In the fuzzball picture, there's no inside the black hole, just more fuzz all the way down. An astronaut crossing the horizon wouldn't notice anything unusual at first, but gradually, their particles would harmonize with the strings around them, like a drop of ink swirling into a cup of tea. The information about their atoms wouldn't vanish, it would just get repurposed, woven into the fuzzball's symphony of vibrations. Hawking radiation, then, isn't random noise, it's the fuzzball's way of humming its stored data back into the universe, one quantum note at a time. Visualizing this is like stepping into a surrealist painting. Instead of a crisp mathematical horizon, the black hole's edge blurs into a fractal-like froth, with strings looping and intersecting in ways that defy classical geometry. Some theorists compare it to a quantum hairball, where every fallen object leaves a unique imprint in the tangle, like fingerprints pressed into an infinitely stretchable material. Even spacetime itself takes on a new texture, here not smooth and continuous, but pixelated by strings, like a digital image zoomed in until you see the individual pixels. Critics argue that fuzzballs lack experimental predictions so far. No telescope can peer close enough to a black hole's horizon to spot the fuzz, but math backs up their plausibility. Calculations show that fuzzballs naturally obey the same laws as black holes on large scales, matching the gravitational pull and light bending we observe. The difference is all in the details. Where general relativity sees a void, string theory sees a vibrating tapestry. Future gravitational wave detectors like LISA might catch echoes of mergers where fuzzballs' unique vibrations ring spacetime like a bell, leaving a signature no classical black hole could produce. The real beauty of fuzzballs isn't just that they save information, they redefine what a black hole even is. No longer a cosmic trash compactor, but a maximal state of quantum chaos, where entropy isn't about disorder, but about how many ways strings can tie themselves into knots. It's a reminder that nature rarely respects our clean categories, and that sometimes the most elegant solutions come not from patching old theories, but from rethinking reality from the ground up, or in this case, from the strings up. The cosmic microwave background should be a perfect, random snapshot of the universe's infancy, a glowing mosaic of hot and cold spots scattered like paint splatters across the sky. But when astronomers mapped it with unprecedented precision, they found something that sent chills down their spines. The universe might have a preferred direction. Dubbed the axis of evil, this eerie alignment sees the CMB's largest fluctuations mysteriously lining up with the plane of our solar system, as if the cosmos itself is whispering that we're not just observers, but somehow participants in its grand design. It started with the Wilkinson Microwave Anisotropy Probe WMAP in the early 2000s. As researchers analyzed its data, they noticed the CMB's quadrupole and octupole moments. The large-scale hot and cold patches weren't randomly oriented. Instead, they clustered around an axis that weirdly coincided with the ecliptic, the plane where Earth and the planets orbit the Sun. Later, the Planck satellite confirmed it. The universe's baby picture wasn't just asymmetrical, it was asymmetrical in a way that pointed right at us. The odds of this happening by chance, less than 1 in 1,000. It's like rolling a cosmic die 1,000,000 times and always landing on the same number facing your backyard. This isn't just a statistical fluke, it's a potential crisis for cosmology. The Copernican principle, the bedrock of modern science, insists we hold no special place in the universe. But the axis of evil flirts with heresy. What if the solar system's orientation isn't random, but locked to some deeper cosmic architecture? One radical explanation suggests primordial magnetic fields or gravitational waves from the Big Bang might have imprinted this axis, threading it through space-time like invisible ley line. Others propose a more unsettling idea, that we're seeing the faint fingerprint of a pre-Big Bang structure, a relic of some higher dimensional physics that set the universe spinning with a subtle bias. Visualizing this is like staring at a celestial conspiracy board. Imagine overlaying a map of the solar system onto the CMB, its planets' orbits tracing lines that eerily match the CMB's coldest and hottest stripes. The alignment is too precise to ignore, yet too bizarre to explain. Skeptics argue it's contamination from foreground dust or galactic interference, but meticulous filtering only sharpens the signal. The axis of evil stubbornly refuses to vanish, taunting physicists with its defiance of cosmic democracy. The implications ripple far beyond astronomy. If the universe has a hidden axis, it could rewrite our understanding of inflation, the theory that the early cosmos expanded uniformly in all directions. Maybe inflation wasn't perfectly symmetric, or perhaps multiple universes bubble off each other at angles, leaving faint directional scars. Some theorists even speculate that dark energy, the mysterious force accelerating the universe's expansion, might also align with this axis, tying the CMB's anomalies to the fate of everything. For now, the axis of evil remains an unsolved enigma, a cosmic cold case that challenges our deepest assumptions. Whether it's a flaw in our measurements, a shadow of new physics, or a genuine crack in the Copernican worldview, one thing's clear: the universe might not be as indifferent to us as we thought. And that's a revelation that's either profoundly humbling or unnervingly intimate. The axis of evil isn't just a cosmic oddity. It could be a glitch in the matrix, a digital smudge revealing that our universe runs on code. Think about the last time you played a video game and noticed texture pop in or screen-tearing imperfections caused by rendering limits or coordinate systems straining to keep up. Now imagine the universe doing the same thing. If we're living in a simulation, the axis of evil might be its version of a pixelation artifact, a subtle clue that reality's underlying framework has a preferred orientation, just like the XYZ axis in a computer program. The eerie alignment of the CMB with our solar system could mean we're staring at the cosmic equivalent of a GPU struggling to render infinity. But simulations aren't the only explanation. The multiverse offers a wilder alternative. What if the axis of evil is a cosmic birthmark, a unique signature marking our universe as one rare variant in an infinite sea of possibilities? In most universes, the CMB might be perfectly random, but ours just happen to crystallize with a slight twist, like a snowflake caught mid-spin. Inflationary theory suggests that pocket universes bubble off endlessly, each with slightly different physical constants. If true, the axis could be a statistical fluke, a reminder that even in infinity, anomalies happen. The debate boils down to patterns versus noise. Simulation arguments lean on the unnerving precision of the alignment, too clean to ignore, like finding a barcode etched into the sky. Multiverse theories, meanwhile, embrace the chaos, suggesting that even the most improbable outcomes become inevitable given enough attempts. Compare it to shuffling a deck of cards, deal enough hands, and eventually you'll get the same sequence twice. Our universe might just be that improbable royal flush, its axis a quirk of cosmic probability. Here's where it gets even stranger. If the axis is a simulation artifact, it implies the programmers left a breadcrumb either carelessly or intentionally. Ancient astronaut theorists might call it a message, skeptics a bug. But if it's a multiverse signature, the implications are equally profound. It would mean our cosmos isn't just one iteration of physics, but a single note in an endless symphony of universes, each humming its own discordant tune. Future observations could tip the scales. If deeper scans of the CMB reveal more unnatural alignments, like layers of directional anomalies stacking up, the simulation hypothesis gains weight. But if the axis remains an isolated oddity, the multiverse might prevail. Either way, the axis of evil forces us to confront an unsettling truth. The universe might not be indifferent. It could be coded, or it could be one in a number so vast even infinity feels small. From the delicate dance of supersymmetries, shadow particles, to the holographic whispers of a hidden 2D code, we've journeyed through 30 cosmic symmetries, each one a rule the universe seems to follow until it doesn't. These aren't just abstract ideas, they're the scaffolding of reality, the invisible walls boxing in what's possible until some rogue phenomenon smashes through them like a wrecking ball. Think of them as cosmic traffic laws. Most particles obey the speed limit, but black holes, they're the dragsters peeling out at the edge of spacetime, leaving tire marks across the fabric of causality. Take CPT symmetry, nature's unbreakable trifecta of charge, parity, and time reversal. It's the gold standard, the one rule even quantum chaos respects, until you remember that the Big Bang spat out a universe drowning in matter, with barely a drop of antimatter left. Or consider the holographic principle, where 3D reality might just be a pixelated projection from a flat boundary trillions of light years away. These symmetries aren't just rules, they're riddles, each one a door cracked open to something stranger behind it. And then there are the symmetries we've only dreamed of, octonions orchestrating particles in 8 impossible dimensions, or the amplituhedron's jewel-like geometry rewriting physics without spacetime. These aren't just theories, they're invitations to reimagine existence itself. Even the ones we've caught breaking, like the axis of evil's defiant tilt, whisper that the cosmos might be grander, weirder, and more mischievous than we ever dared to suspect. So here's the real question: which of these cosmic rules or rule breakers stops you in your tracks? Is it the fractal universe nesting inside itself like infinite Russian dolls? The time crystals ticking defiantly in the quantum cold? Or the black holes that might be fuzzballs humming with the data of everything they've ever swallowed? Drop your favorite in the comments, because the wildest part isn't just that the universe follows these symmetries, it's that somewhere, somehow, it's already bending them. Now watch closely as we zoom into the void, through galaxies, atoms, and the shimmering edges of a fractal cosmos, where every layer hides another twist, another broken mirror, another secret waiting to crack open. The universe's rules are written in smoke, and we're just learning how to read the